All right. Last time. Let's see what we did last time. Let me just run the game. Oops. So, we have this game where we can jump around and stuff. And last time we added some cool physics when you walk by these flowers and grass and stuff. They bend a bit. So that looks cool. That looks cool. And I thought today, maybe I think I want to add some kind of particle system. Well, not necessarily a particle system, I think, but just some small particles flying around. Because I think we can get some cool interactions with this velocity vector field that we made. The same one that's used for the plants here. So if we walk around, the particles could also move along with the player, like looks like some pseudo wind almost. Yeah. So some kind of particles. I think maybe a good first particle, like maybe if you walk around, maybe we want to spawn some dust, maybe some dust particles, small dust cloud, or if you land on the ground, maybe we can spawn like a puff of smoke or dust or something similar. Maybe also just some small like ambient environmental particles to make everything look dreamy or something like that. All right. So I guess we'll start by just adding some file where all of these particles will live. Let's call that particles.h, right? And let's have some struct for the interface, started particles, and we want a way to create the interface as usual, and destroy the interface afterwards. And we most likely want to use the Vulkan interface instead of this particle system thingy. All right, waste isn't highlighted. Right, okay, it was. IntelliSense is a bit slow. All right, so first, let's define or let's implement this struct. And for now, I guess we want to keep a reference to the Vulkan interface. So we'll add that there. And let's allocate that structure. Check for out of memory, right? And then we just assign this Vulkan interface for later. We will probably need it. So, and let's see. So, for now, I'm not gonna be updating the actual particle state on the GPU. So we'll just make a particles tick function that will simulate one time step of the particle logic, right? Yeah, and we want to let's see. Yeah, we probably want some function to draw the particles. However, let's call it particles render. And let's see if we need a command, the Vulkan command buffer. I don't think so, actually. I think that should be enough. Let's see, because this render function will probably not do the actual rendering, because like all draw calls right now is inside of this scene.c file. Like here's the draw calls for the world, which is this grass and whatever, and we're probably gonna place it in here, right? So this render function is just gonna prepare some data, basically, for the drawing, not do the actual draw call. Right. And I think a good direction to start this from is to start with the actual sprite rendering. I imagine that every particle is gonna be, it's basically gonna be a sprite, right? Or a billboard. But I'm not sure if the term billboard is useful in 2 dimensions. Maybe we should call it a sprite. But basically a rectangle, right? And we don't have textures right now. We will ignore textures for now. So I guess we'll make it like a solid color quad. With some size and maybe rotation, actually, also. But I think we'll start from there. So I think we will start with like getting a single particle, I guess, drawn to the screen using this billboard stuff. Okay, so for that, maybe it's actually best to start from the actual shader. I think that makes sense. Then we'll see what data we need for the actual rendering. So let's call that particle.hlsl. Right, and that's going to need a vertex shader. And we need some input into that vertex shader. And I'm wondering, I probably I'm wondering if I should just fetch the vertex attributes myself. Yeah, I think that's easiest, always. So in here we only want the vertex index. Or is it vertex ID? The semantic is vertex ID, right? I can check the world real quick. Yeah. Okay, so I will call it vertex ID as well. Right. Okay. Let's take this v's input into this vertex shader. And we need a fragment shader as well. Right. So the vertex shader should output something as well. Bare minimum is outputting the position like that. And for now, probably maybe the color also. Yeah, let's make that a float 3. And in here, I'm gonna take a look at how I did this in the world. Yeah, right, so we'll only define the output. Because the input to the fragment shader is basically always gonna be this, the output from the vertex shader. So we'll use the same struct here. Right, like that. And let's zero initialize that. I like that. To do that. Okay. And we'll do the same here in the fragment shader. Right. And for now, the color is gonna be the exact same color that we get from the vertex shader to start with. Completely opaque, 1.0 alpha. Right, and now I have this separate script to compile all of my shaders. And I will add this here, so we have particles.hlsl. We'll create a particles sphere v. Right. That should be it. So let's try building it. Particles. Particle. Yeah, let's make it singular. Singular. Let's see. And I probably goofed up here. Yeah, and this should return the VS output. This should return the FS output. Okay, compiles, but it doesn't do anything right now. So let's see. We're gonna need some kind of world space position of each vertex, right? Right. Now the question is though, if we're drawing a rectangle for each particle, the GPU can only handle the rasterization stage of the GPU can only handle triangles. So a rectangle is 2 triangles. Right. And we can do a bit of trickery here. I think we don't have to actually send the position for each vertex from the CPU. We don't have to write that data, I think. The only thing we need is like the center. We need the center point of the rectangle, and possibly the width and the height, right? And some rotation. And we can figure out the position of these 4 vertices inside of the shader itself. We basically expand it from that center, right? So that's less data to transfer. So let's see how I would do that. I would use non-indexed rendering. Yeah, I would use non-indexed rendering. So there's gonna be some redundant work, but I think that's fine. So we will have 6 vertex shader invocations for each rectangle or quad. So we'll have something like the, let's say, local index. Okay. Yeah, let's call it local index. And depending on this index, we are going to be at some different corner of this rectangle. Yeah. And for now, let me just how do we figure that out? For now, let's just do a switch statement here. So we have 6 options, right? So I'm thinking this would be the, yeah, let's say this is the bottom left. And let's make that like so. Right, bottom left. And then we have the bottom right. Yeah, let's make it the bottom right. Well, no, the top right. Yeah, let's make it the top right, because we want the. Oh well, the winding order doesn't matter. Okay, it's mentally easier if I do it the bottom right. So bottom right, and then top left. Okay. I could also write this out, right? So bottom right, bottom left, bottom right, and top left, right. And this is the next triangle, second triangle. So for that one, we will start at the top left. So same values. Top left, and then to keep it in the same winding order, like counterclockwise, we will do the bottom right, yeah, and then top right, yeah. So bottom right would be, yeah, that is already correct, right? And the top right would be both positive, yeah, because my x-axis is to the right on the screen, and my y-axis is upwards, right? So minus minus along both of those is the bottom left, right? For example. All right, and we should break after all of those, right? So if we now issue a draw call with this shader, right, with 2 triangles, we are basically constructing a quad, right? Right. So now, if we know, we should know the size somehow of the particle. Let's hard code this for now. And so the position would be, okay, so we will have some kind of center of the rectangle, and let's also hard code that for now. Let's make that 2, 2 maybe. I'm gonna check. So here's our origin of the world. So this is 0, 0. So 1, 1, 2, 2 would be here somewhere. Okay, I think that's fine for testing. Right, so we hard code the center right now as well. So the position of the vertex that we are handling right now would be the center position plus this corner that I defined times this size times a half. Right. So then we have the world space position of each vertex. Makes sense. And now I just have to write that to the fragment shader, right? And the color. And for now, let's hard code the color as well. To purple, pink. Right. And projecting this onto the screen, we're gonna need the camera view projection matrix, which is inside of my frame constant buffer. So let's include that as well. Right. And I can just copy paste how I did that in the world shader. That's gonna be exactly the same. We just want to take some world space point and put it into onto the screen, basically. More or less. Right. So do that exact same, and this is just some some trickery. We have to do this basically. Okay. So we just put that position on the screen. And we have to include the GPU types header in the shader. Alright, and the particle... Oh, I wonder, the particle should probably have some kind of depth. Right, it should probably have some kind of depth. For the moment, let's do 0 for that. We could put that in a variable as well to make it more clear. We should probably get that from somewhere later. Okay, but that shader seems to compile. Now I just have to add that to the game also, and the speed so we named it particle.vs speed. So these SPO files, those are so what's it? It's particle .vs SPO, for example. Wait, did I forgot? Oh, right here, yeah. So that is just an ELF object file, right? And it contains the compiled SPIRV inside of it. So we basically embed these shader files into the program with this LD. No, never mind. We just add them right as input to the GCC command, so they get put right here. Yeah, just like the C object files, right? Okay, so we have those in the executable now, embedded, and we have this shaders .h, where we'll just add that also as an enum. Particle, vertex and fragment shader, yeah. Yes. And we have to add them in a bunch of places here. And this basically just creates the Vulkan shader module object from this sphere V, right? That's embedded into our executable. And yeah, it still runs, that's good. So the shader compiles. And now, since everything is hard-coded into the shader, we can pretty easily try to draw this particle. But first, we have to create the pipeline. And I guess we could actually create a pipeline inside of the pipeline C file. I think that would be nice to keep it like in the same place potentially. Maybe we'll do that later, but for now I do it here inside of this scene. And yeah, I will keep it here. Yeah. Yeah, it doesn't really matter, right, where it is. It's only for like convenience and code ergonomics, I guess. So we already have this world pipeline. So let's create the particle pipeline and all of the other stuff that's required. And we just have to copy paste this whole function that creates the world pipeline, and we'll swap out some stuff. So this is the bindings that shader is using, and right now we only use the frame constant buffer, so we only need this single entry here. And there's going to be a bunch of search and replacing to do here. Particle, let's call it particle, yeah. We call it particle. Like that, and use this new particle shaders also that we defined. Like so. Most of this should be identical actually. I don't think we have to change a lot here. But we'll take a look. Color mode none, I guess that's fine. Triangle list, yes. Blending seems fine. Depth right enable. I'm unsure if the particles should write depth. I'm thinking they're mostly gonna be semi-transparent, right? So let's not do that for now. Yeah, and this is gonna be the same. Create a particle pipeline finally. Right. Did I forget anything? Yes, I missed that. Alright, that should be it. Now we just have to call this also. Right, that's it. And now we have a particle pipeline to draw with. So, since we did all of this magic in the shader, yeah, like I mentioned, everything is hard-coded. So if we just draw 6 vertices right now, we should actually see a particle. Yeah, we should see a particle without having to send any data at all to the GPU, except for the actual shader code itself, right? So we'll just do a draw call on the command buffer. Let's see, 6 vertices, 1 instance, 0, 0. Alright, and we also have to do all of this stuff. So we actually have to bind the descriptor set and the actual pipeline, of course. So instead of the world pipeline, we'll bind the particle pipeline and the particle pipeline layout here. Right, and we create a new descriptor set that only contains the frame uniform buffer. Yeah. That should be it. Let's see. Okay, there's nothing. Nothing. I forgot to replace this. Okay, that should also be replaced. Okay, we don't get any validation errors, but there is no particle. That's interesting. 1 instance, yeah, okay, so this looks correct, I would say. So what about... Oh, I did the wrong thing here. I should do modulo, right. Right. Okay. There is a particle. Amazing. Yes. But everything is completely hard-coded, right. So, this is the data that's hard-coded right now. So, we just have to get this data into some buffer, right? So we can actually read these values instead. Yes. And I am thinking. Yeah, for now let's just put the center and size in there. Let's still ignore depth. Let's ignore depth for now. So I think we'll define this type in our GPU types header. So we'll have something like maybe we want to prefix it with GPU like we did for everything else, so that we know it's like a GPU type, I guess. So GPU, let's say particle yeah, we can just call it GPU particle. I guess that's fine. That's fine. And we'll type def it for C. Alright, so we need the center. And we also want the size. Yeah, so this is the diameter, right, of the particle. And the size of this one should be 12, right? 12 bytes. If I'm not mistaken. Wait. Okay. Oh yeah. All right. That's that. So let's start in the shader again. So we can now bind a new buffer here. Create a new binding, and let's actually. I like using byte address buffers because there is some unexpected, let's say, padding problems sometimes when you don't align stuff to 16. So I want to make that a non-concern when I do stuff like this. So let's just call that particles maybe. So this is the particle buffer, which contains this struct. And to get this size and center now, we just have to load this particle data with the load function on this buffer, and the index we want to load is going to be the particle index. And that's the vertex ID divided by 6, right? Yeah. And this is actually loading from, you specify the offset in bytes inside of this buffer of which to, like where to load. So this is in bytes, we have to multiply it by the size of this. Which should be 12. Yeah. Right. So yeah, for each particle we have 6 vertices. Makes sense. So if we would like to draw 2 particles, for example, we would just do, 12 here, right? Or 6 times however many particles. Right. So for now, maybe we can actually start with... So when we're drawing this stuff, we usually have these structs, right? For the world, for example. The world has these flowers, right? And it has the ground here. And that's just some vertices in a buffer also. And the way we get this is through this world render info struct. So we'll just create a similar one for the particles, and that's just gonna contain like some data that we need in order to actually draw these particles correctly. So we'll have something like particles render info. Sure. I'm not sure if we should use singular or plural. Particles render info, let's call it that. So what we're gonna need here is then, I guess, the particle count, right? How many particles we actually should render. And we also want this particle buffer, right? We also want that. Yeah. And then we just want some function to retrieve this data. So we'll have like a particles get render info, right? That outputs this info. Equals particles. Seems fine. Right. So where do we actually get these numbers from then? Well, we actually need to create this particle buffer first. So the particle system or whatever will have this particle buffer. And actually, I think for simplicity, we can make this a buffer that lives in system memory, right? So we'll have the particle buffer, and since we're also gonna have this buffer mapped, then we'll also have the particle buffer memory, right? And we have this place where we allocate staging memory. Here, okay. So we have a bunch of subsystems that allocate staging memory, and we just want to add our own function here. So instead of this, whatever, so we have particles alloc staging mem, right? And we haven't actually created the interface yet. I guess we can do that. So we'll include the particles.h, and let's just create it here. Particles create. Like that, and we should, I'll copy this signature here, and let's actually create this function. This probably doesn't have to return anything, actually. Okay, so instead of wind, particles alloc staging mem. Alright. And for this interface, we actually need to include the staging memory.h. Like that. And we need a separate memory, like, region, or a separate buffer for each frame also. So we need some concept in here of a frame. So I guess that will be something like the particles frame. Yeah, that's fine. So this data is actually going to be per frame. Otherwise we will have some data races when we write into this. Right, so we have some frames. And we actually have this defined somewhere, the frame count, which is in common, I think, common.h. Yes. So we have some number of frames. Alright, now we can actually start doing stuff here. So we want to push a staging buffer allocation. Right, and we should do this for every frame, so... right, let's pull out this particles frame here. Like that. And we'll allocate the frame particle buffer. And the frame memory pointer. Right, and the size of this. I guess we will just create some kind of, or define some kind of max particle count, I guess. And let's make that 64,000. Seems like a good number. 64k. So then we should know how big this buffer has to be in the worst case. So we'll have the particle buffer size, which would be max number of particles times the size of this structure we made right? And that's called GPU particle t. Did we actually include the GPU common? I think we have to do that, and that's in the shaders folder, right? So GPU types, right? GPU types, because that's in there, right? So now we know this size. The buffer usage. This is going to be a storage buffer, because we want to read from this buffer from a shader. And that's all, basically. That's all. Nothing more, nothing less. Because we're actually filling this buffer from the CPU, right? Right. And we'll call this particles. Right, so we have that actual buffer now. Yeah. And now, in this render function, we actually want the render context, which contains a bunch of useful stuff that you might want for rendering, such as the frame index, which we will need, because the particle buffer that we want to fill is gonna depend on this frame index, right? We need to know which frame we're rendering. So we get the frame with that frame index, and here we have the buffer memory, right? All right. So that buffer contains GPU particles. So let's say we'll just cast it like this. So now we can easily write particles into this buffer. Why is my IntelliSense like that? Oh shit. Oh. I named this. I named them the same. Okay, that's annoying. Maybe naming these particles wasn't the best idea in the world. But all right, let's call it P, I guess. So if we say that, I guess let's fill some particle data. Right? Let's fill some particle data. So let's say that the size of this particle is 0.1, and the position. We can do some fancy. We can do some fancy math here, I guess. Let's make it spin in a circle or something like that. So we'll just need the math header. Let's take the sign. Oh, we don't have. I used to have the total elapsed time inside of this struct, but I don't anymore. Okay, well then, let's just keep our own time, I guess. Whatever. So we'll have some elapsed time in here. Right, and when we tick, just add the, we have the time, wait, delta time, yeah, because we have a fixed time step, yeah. Makes sense. So then we can use that here. We probably have to scale it down a bit, or it's gonna be very fast. Like so. Okay, so we should have a spinning particle inside of this buffer now. Yes, we should have a spinning particle. So now... So I guess one issue now is that inside of this function we also have to know the current frame, because we want to assign this particle buffer, right? And that's inside of the frame. It would be something like this, right? And the particle count right now, we only have one, because we're filling one here. Right, so we could just take in the frame index here, right? I mean, yeah, why not? Why not? Seems fine. Seems fine. So now we can go back here to where we actually render the particles, and we will get this particle render info. Like that, and I guess we also have to include. Wait. Hold on. I guess we actually have to send this this particle interface to the scene in order to do this rendering. So let's include the header, and yeah, let's just send it like that into the scene render context. Alright, so I guess we can also check here, right? So if we actually have any particles to render, then we should render some particles. Makes sense to me. So we'll render 6 vertices times the number of particles. Yes, and now we also have to bind the storage buffer, the particle buffer. And actually we could just send we could just put this here actually. So instead of sending the VK buffer, we send this descriptor buffer info. I think that's nicer. So we'll do this here instead. So we have VK descriptor buffer info, and that contains, let's see, that has the VK buffer and the offset and the range. Okay, so the offset is going to be 0, and the range we can actually use the particle count to figure that out. Yes. So that's going to be the particle count times the size of this GPU particle structure, right? That's the range, byte range of the buffer that we want to bind. Seems fine. So now if we go back here, this is going to look a lot nicer, I think. We just do it like that, pass the particle buffer here. Awesome. And now we also have to add it here actually, to this list, because we're binding the uniform buffer, and now we're also binding the particle buffer, which is a storage buffer. Segmentation fault. Classic. What could the issue possibly be? Right, I forgot. Wait. We have this scene render context, right? I forgot to actually pass the particles interface. Alright, and I also forgot to add all of these like tick functions and render functions, right? So let's do that after this. So we'll have the particles render. Okay, we have the render context. I create that below, okay. And we have to tick the particle simulation also, right? So let's add that. Particles. Tick that after the wind simulation. Okay, this should be const, I guess. Const render context. And let's skip GDB. Okay, it's... Did I actually... Wait, hold up. In the shader, I didn't actually use this. So now we have the size and the... did I call it center also? Right, that's working. So we have this particle spinning around in the unit circle. Makes sense with the math we made. Okay, so that proves that we can fill this buffer with some particles, and we can draw them. I guess doesn't actually. Let's draw. Oh shit! Wait, hello. My GPU almost died. Alright. Ignoring that, let's try to draw some more particles than just a single one and see how that works. So where are we actually filling this? Right. So let's try to draw some number of particles. Let's say 64. And we can, let me think, let's do some randomness here. Let's do some randomness. So take some randomness. Let's, yeah. We take some randomness and scale our two components, and we can also take actually some more randomness well, let's try this first. Okay. We're still drawing one, right? So we have to draw 64 once. Okay, that's definitely 64 particles. But it doesn't look as interesting as I expected, so let's randomize the time also a bit. or the time scale here. So this is going to be 0 to from 0 to 1. So let's divide that by looks like 100, right? Well, maybe, yeah, let's say 100. Yeah, let's do that. Let's wait. So plus 0.01f. Okay, that's, and use that here. That's gonna make it look interesting, I think. Yeah, it looks somewhat interesting now. Let's actually make it a bit slower. Even more slower. All right. So we have the ability now to draw some particles, right? We could also try to actually we can do something fun with the size also, with the scale. So let's do some more randomness. So the size right now is 0.1. Yeah, let's add some randomization to that. Oh wait, so t plus. Let's do something like this. I think they are scaling. Yeah, they're definitely differently scaled right now. Okay. Okay. So now, I guess we want to make some actual interesting particles. Well, this does look very interesting, actually. Intriguing. It could be something like... It could be something magical, right? Or something. Definitely, definitely. Ooh, well, I guess something we could add. Let's go to our particle type. And let's add a color to the particle. So right now, yeah, we hard-coded that also to pink. But let's... okay, we need to actually unpack it, right? I should probably put that function in a shared... let's copy-paste it. Let's copy-paste. Right, so we'll have some function to unpack particle color, right? Like that. And for now, I guess it's just gonna be all black, right? Yeah, so they're not... You can see them a bit in front of the flowers here. But yeah, they're completely black because we zero initialize those particles, right? When filling. So let's add some color. And we can use this scale. Let me think. Yeah, let's do something like this. So something like that, and let's add some red. I guess. Let me think. Let's use this. So that's a random value. So let's scale it down, add up. So that's from 0 to 1. 0 to 1, let's multiply that by 255, right? Cast that to an int. That should be it. Yeah, we got some. It's not really that noticeable though. Which is a bit surprising. That should be a value from 0 to 1, right? And that's also... try the green one, and let's make that inverted. Let's see what we get. Okay, yeah, that's more noticeable now. Right. I guess this could actually be like some kind of particle effect in the game, right? Looks like it could be spinning around some legendary item pickup or something like that. It looks magical in some way. Looks pretty cool. Mesmerizing. All right. Now what? Yeah, we could try to make some proper particles, I guess. So I'm thinking, let's say that we would like to spawn maybe some dust cloud maybe when we're walking. Let's say our player's feet impacts the ground, right? And we make something, some cloud of smoke or dust appear. Right, so how would we actually want to... What kind of API would we want in the game to do that? Is the question. We probably want to have some concept on a high level of like a particle effect or maybe particle effect type, right? Let's call it particle effect for now. So we'll have something like a particle effect. So let's call it dust let's call it footstep dust, right? So when a footstep occurs, we want to spawn the footstep dust effect, right? So we want some API called maybe particles spawn, maybe. And we want, I'm considering making a struct for this data as well. I think that's nice. So we'll have something like a particle spawn, maybe. So we'll have the effect, and we should probably have some position, right? Let's call it pos. So we'll take in this spawn data. Yeah, let's do it like that. That's nice. Right. I feel like that makes sense. And I would like actually to put that maybe above the render info getter. Right, and we of course I forgot to pass this interface first, obviously. Okay. So now let's say when we step on the ground we want to spawn a small dust cloud. So that's maybe gonna be some number of particles, right? Maybe 8 or 16, whatever, doesn't matter. But we need, and I imagine these are gonna like maybe be visible for 1 or 2 seconds, right? And then slowly fade out and stuff like that. So we need some kind of state for these dust particles, right? They're probably gonna have some position, most likely some lifetime, right? And yeah, most likely some lifetime and like how long they should live, right? Yeah, I guess we can just start by creating that data, right? We'll just add that into struct, I guess. So we'll have something like the, yeah, so we call it footstep dust. So let's call it footstep dust particle. That's gonna be 1 particle. So it will probably, right, have a position, and it will probably have some velocity. Probably, yeah. And what more did we say? It should probably have some what should we call that? Lifetime, like how long it should exist for, right? And it should have an age. So this lifetime would be expressed in probably milliseconds. We use milliseconds a lot, especially in the float time. So we'll have some millisecond length of how long the particle should be alive for, and this age is going to be how long it's currently been alive for. So we can easily know whether it should be killed, right? If the age is greater than the lifetime, then we should kill it. Makes sense. And in this particle system or whatever, we're gonna have to store this state somehow. Footstep dust particles. Let's call it that for now. Like so. And we need to know how many of these we have, right? You can probably foresee some potential drawbacks with this method, which we'll see how bad this gets once we add more particle types, right? At some point we maybe have to generalize particle logic somehow, but we'll cross that bridge once we get there. But for now, we just have some list of footstep dust particles, right? And let's just allocate some number. There should probably be some. I guess we can put that limit here. Maybe we can actually create some kind of let's call it particle effect info, maybe. And in there we will have the max count. Yeah, and then just make a list of all of these infos. Particle effect info. Let's call it that. And we're gonna have one for each effect. So we'll keep track of the number of effects we have with this enum entry. Like so. And we can initialize this with a nice designated initializer list. So let's say that we have a max of 1024 of these footstep particles. And what's the problem? It's just the IntelliSense. IntelliSense is the problem. We could probably also generalize this allocation actually, but let's just raw dog it for now. So we have the number of particles and we know the size of each particle. Right, we could just put that in here also, like the data size or something like that. And just do a for loop here. But whatever. Okay, so we have this memory now for these footstep particles. Right. Did we implement this? Yeah, we have an implementation for this. So, now, I guess we will just... we could just... Oh god, Jesus Christ. Check which one it is, right? Check which effect we want to spawn. And if it's the footstep dust, let's create a specialized function for that. Spawn footstep dust. Right, that's all right. That is all. We only have a single one. Right, so in here, we now have this. So I guess when we take a footstep, we want to spawn some number, right, of some number of particles. Let's make that a random value. Let's say between 5 and 10 particles. Seems good. Right. So for each particle that we want to spawn, now we can just fill out this data, right? So age should be 0. So that is fine. Let's make it simple and let's say that they live for 1000 milliseconds, which is 1 second, right? And the position, let's make that the spawn position, and we can add some randomness to this. So let's take some random value between 0 and 1 and scale it up by 2, so from 0 to 2, and subtract 1. So from -1 to 1 is our random value. So let's take the spawn position and add this in the X direction. Yeah. And the Y, let's always make that the spawn position. Right. And the velocity. I guess we can use this same random value that we created here. So from -1 to 1. I need my vector math functions now. We want the velocity to be... Oh, well, it doesn't matter if it's normalized or not, right? Okay. But the X will make that just this random value. So the same direction that we spawned it in. And maybe we should scale that down. I don't know. Let's do that. And it should probably move upwards a bit. If it's like smoke, like if it's a dust cloud, it should move upwards, right? Right. And all right, we also have to actually start writing, because if we already have particles in this buffer, we have to start writing at the end of those, right? So let's say that we have we just take the particles and just offset it like that, and then we will actually spawn into this buffer, right? And we can't call it particles. Let's call it spawn particles. Like that. Okay, so now we create some data for these particles. And we increment this particle count. Yeah. That should be it. So if we now call this spawn function, I guess let's actually do that in the game. So when do we want to spawn footsteps of the player? We probably want some timer or similar. So let's call it footstep timer. Yeah. Or actually, no. Let's just let's keep like a last footstep. Let's do that. So we have a last footstep, and that will be the position of where we took our last step. Okay, so how we can tell then if we want to spawn a footstep is just to check the distance from from the current position. Right? So if we tick the player movement, so after we do that, this game state is completely useless right now. Let's ignore it. So after we tick the player movement, we can check. We should probably keep that inside of the player, right? That makes sense. So the player has some last footstep position, right? Okay, so then we can just check the length. Let's actually make a new helper that's called vec2 distance. So we can check the distance between two vectors, A and B. And that is just subtracting A from B. Well, the order doesn't matter at all, right? And we take the length of that. The length of the difference is the distance. Makes sense to me. Right, so now we can check the length between the player position and hello? Okay, last last footstep. And why? What is up? What is up? Oh. Oi, 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 oi. Never mind. Vector distance. What is the problem? Is it just? Oi, I'm stupid. Right, we should use the correct function. Alright, so we will have some kind of distance here. Right, and we can just, well, we don't, we can just check this distance. If it is greater than some distance, we can make it 0.2 maybe. If that is the case, then let's spawn this particle. So we need that interface, right? We have to pass it when creating the game. Yeah. This is starting to become a lot of arguments now. Right, and we will just hold on to that. Hold on to that interface, so we can call it here. So we'll do particles spawn, right? Yeah. Yep. So, pass the interface. And the spawn structure, and the effect should be the footstep dust effect, and the spawn position, that should just be the player position. This position is at the feet already. Okay, so if we start the game now, we're actually not gonna see anything. Because we're not drawing these particles. We are not drawing these foot particles, and there we ran out of space in the dust particle buffer. And I also forgot something. We have to check if we are actually on the ground also. And I guess we have like a is grounded, right? Yeah. So if we are grounded, right, we just have to check that. Because we shouldn't be spawning stuff in the air. Right. So I think we should actually. So we have some number of these particles now, and now. I guess we can start actually with the rendering of them. Yeah, let's do that. GPU, let's call it this GPU particles. Okay, so here we can keep these actually because it looks cool. So just add 64 to that, so and then we can start writing the actual dust particles in here. So for that we should obviously go through every dust particle, I guess, which we have in here, the count, right? And let's see how we get this data. So the center of the build board, let me actually let's fetch this dust particle state. Let's call it dust particle. Right, the center should be just a position, I think. And the color, let's make that brown. And brown is like red and a bit of yellow, right? Let's try that. I think that's brown. I think that's brown. And the size, let's make that 0.1. So now, if I go into the game, I think we're actually gonna see something. There is nothing. There is nothing. That is suspicious. Suspicious. Let's scale this down a bit. Maybe that's the issue? Well, 1 meter is a lot, right? So this is gonna be 1 decimeter, right? Yeah, there's still nothing. And we do have particles because, yeah, we crash, right? Interesting, interesting. I guess I could... we can make this a bright color to see if... Yeah, that's not the issue here. Right. This particle count. Yes. Maybe it would be nice to actually just keep that in the particles here. So we'll have something like the GPU particle count, right? We could keep that in the frame, sure. So when we actually do this rendering, then we'll start by just initializing this to 0, right? And just do this. And when we're done filling the dust particles, we will do the same thing, but with the count here. And then we should just use this frame GPU particle count. That is working. There is some dirt particles here, but yeah, they're not being killed. They never disappear, and they don't move either. So we'll have to add that logic here. We'll do that inside of the tick function here. So we will once again go through every dust particle. It's basically gonna be the same, right? Except that now we're gonna modify the internal state here, right? So. How should we do this? I think actually we want we can start by let's just start by moving the particle along by the velocity that we created, and we have to scale that by the delta time. So now they should move. That was extremely fast. extremely fast, so scale that down a bit. Okay, that is more like it. That's more like it. It's, however, not very random, and we will fix that later. Because we use the same RNG state everywhere now, and we reset it and shit. But that looks a bit better. Be right back for a moment. I am back. Alright. Now what? Right, I was doing some... I was updating the state of each particle, right? Right. And that is working. Right. Except... Well, it's... Okay, wait, hold up. I've actually forgot... Right, after I actually spawn these, I have to change where the last footstep was, right? It's just spawning forever now. That makes sense. Let's see now. Yeah. Right. Alright. That works. So now there's not, it's not spamming particles. Right, and at some point, these particles should actually die. So, at every tick, we will increase the age of each particle by the delta time, and then let's call this is alive, or is dead, maybe. Is dead, I think, is more appropriate. So if the age is let's make that greater equal. Yeah, if it's greater than the lifetime, then the particle is dead. And we need stud bool. Stud bool. For that, I think that is the issue, right? Okay, so what should we do if this particle is dead? We want to remove it somehow, right? We want to remove it from this list. And right now, I'm not going to care about actual about maintaining some order in this data. I don't think that matters. So what we are going to do, first of all, if we like delete the current element, we don't want to increment the actual index, right? So we only want to do that if the particle is alive, then we should just continue on with the next one, right? However, now if it's dead, in that case, what we should do is pretty simple. We just decrement the number of particles we have, right? And we also replace the current particle that we're processing. We replace that with the last particle, which is now going to be this new count, right? We replace the current one with the last particle and decrement the count. Right, so the next step, we will be loading this same index again, but now it will be a new particle, right? I feel like that should work. Yeah. So now these particles actually disappear after a while. I guess I set it to something like 2 seconds, right? Right, and now the problem is that it looks very boring. Very boring. So, because we are using the standard library random number generator, and we actually it uses like a global. It's global, right? So, and at some points I want a consistent randomness, so I just set the seed sometimes in some random places, like basically every frame, right? So we should probably have our own kind of random number generator state in here inside of the particle system, and a very simple type of random number generator is a I'm not even gonna try to pronounce it, but it's not the Living Church of God, but it is a linear congruential generator, and this is very easy to implement. Right. It's this. This is the formula. Right. Very simple. So the whole state of this random number generator is a uint, right? So for now, let's just have one randomness state for the whole particle system. So we will call this RNG. That's just a unit, okay. And we need some functions to, I guess, I wonder what we should do. Let's call this LCG rand, and we just pass in the state, and we get well, maybe we can just use this one like in sequential. So all we need is this, which basically just updates the state of this random number generator, right? And that is done according to this formula, right? So, oops. So the next state is defined by the current state multiplied by A . And does it say what these mean, actually? Right, A is the multiplier. So we have something like LCG multiplier, right? We have the multiplier and the increment. Okay, so the multiplier, let's actually use the glibc implementation. Yeah. And we have the increment, which is 1, 2, 3, 4, 5. Right. Okay, so the result is bits. Okay, so you don't actually use all bits to get the actual number, apparently. Let's check that. Let's check that. Actually, we can check the. So there is like a random max, right? So what is this random max? Okay, so it is actually int max. Output bits of seed in rand. But if it's same as int max, right? Okay. Right. So modulus. So wait. Okay. Well, let's actually we can. Let's pick this one. Let's take this one actually, because then we don't have to do anything fancy. That's easy. That's good. That's gonna be simple. So we use this one as the multiplier. This as the increment. Right, and it's just gonna be the full thing, right? Good. Perfect. So we take the multiplier and we just add the LCG increment, right? And I will add parentheses to make it more readable. Yeah, okay, maybe, okay, I guess it would be nice to actually, like, just return this new value. Let's do that. And that's all, right? Multiply by the multiplier and add. Yeah, and the mod M is 32 bits, so we don't have to do that. Right, so we have this randomness now. Alright, so instead, okay, so here we actually want a stable randomness for this test case here, but here we actually do not. So now we do the randomness here with this RNG, like that. Yeah. Yep. And that's it. Now it should look a bit more random. Yeah, it looks more random. It seems a bit biased. It seems to be more to the right. Oh, I am okay, stupid. Okay, so we actually want to float here. Okay. Never mind. So let's add some kind of function to get a random float. Let's call it rand_f, and that will be a float between 0 and 1. So for that, we just call this randomness and 1, 2, 3, 4, 5, 6, 7, 8. Right. Right. That should be it. Because randmax is not the correct thing here. Okay, so now we get a random value between 0 and 1. Yeah, makes sense. Okay, now it looks more even. Okay, good. This footstep, there are too many footsteps, I feel like. So, what distance did we take here? 0.2. Let's try 1 meter. Okay. I want to make the particles a bit bigger, actually. Where do I draw them? Okay, so, right, they have some velocity. I want to add some kind of damping. However, it would be nice to have some randomness function that returns a floating point number between a range of numbers. So from A to B, right? So to do that would be pretty simple. We just use this randf that we have to get some value between 0 and 1, right? And then we will lerp man, it would be nice. I guess I will add lerp in here. It's kinda, I don't have a better place, so let's call it lerp f. Yeah, so that's gonna be a single component vector function. Lerp f. And that's, yeah, it's just this. This is the lerping function. A. Okay, so it's A. BA, right? Yeah. Alright, so we just lerp between A and B using the factor T. Okay, so now we can get a random number between a set of two numbers. Because I wanted to like get some random velocity here, and it's a lot easier if I can specify the range. Okay. I want to add some kind of damping, because if you imagine like a puff of smoke, the initial velocity is going to be high, and then it's going to dissipate over time, right? Somehow. So let's add some damping to the velocity. So in the tick, we can just, after we add the velocity to the position, let's just take the actual velocity and scale it down by some percentage. Okay, that looks kind of physically accurate. That doesn't look too bad, actually. I would say that the initial velocity is maybe a bit high. Yeah, and now I think the only visual problem here is that it would be nice to have them semi-transparent, I think. But we can try something a bit simpler first. We can try just scaling down the size as they disappear. Right, so now the size is hard-coded here. So it would be nice to have some factor. TH T. Agate, TH. TH, that's fine, okay. TH, which is like the factor. Like it will be 0 when the particle spawns, and it will be 1 when it dies. So some kind of normalized lifetime factor, right? And we can figure that out by looking at the age and divide that by the lifetime, right? Then we know how far along we are in the life of this particle. And then I will just lerp down the size of the particle with that factor. That looks pretty cool. So now it's not like abruptly disappearing. It is a bit like abrupt when it actually spawns, though, I guess. I really wonder how it would look if I match the exact same color as the ground. Let's see what color that is. It's this color, a bit darker brown. I think it could really benefit from some transparency. Because right now it's completely covering these plants, right? So I could try. Or what if I put them behind the plants, actually? So I think if I just increase the depth a bit, that will happen, right? Yeah. It's not as behind the grass. It's like barely visible now. It's barely visible. What if I maybe decrease the speed of the player? It's barely visible now, and yeah, I'm not sure yet. Like if the player itself, the player obviously doesn't have a sprite right now, or some kind of representation, except for this debug box. But maybe the player should also be behind the grass. I haven't thought about that. So maybe it makes sense if the dust is behind the flowers. Maybe. But it's like, it's barely visible, right? But maybe that's good. It shouldn't be too distracting, right? Maybe it's good. Maybe. Alright, but that's some fully functional, functioning particle effect, right? And we could do a bit of cleanup, but maybe we can commit this current state. So I should probably hide this debug effect, even though it looks cool as shit. Yeah, okay. It's barely visible though. Oh. But that's... oh. It's probably fine. Let's actually not hide that particle effect. It looks very cool. But that's some good progress. We can commit that. So I guess that would be particle system. First version of particle system, maybe. Right. I think I would like to add some kind of maybe ambient effect, like something you see in a lot of games. I think, at least. I've seen it in Dark Souls. I know that, like in this magical forest, there's like some glowy, like small dots almost. Like maybe it's like supposed to symbolize maybe pollen or something like that. But adding something like that, they just basically, I guess, yeah, I wonder what the spawning would look like. Like, it would be like maybe kind of all over the air, right? Some small particles. That could add some ambience. Maybe they could spawn from the ground or something like that. Maybe. And something like that. Like that's a completely kind of different, right? Because that would not be... the spawning of those would not be controlled by the actual game logic, right? That makes no sense, I feel like. That should be completely, I guess, internal to the particle system. So I don't even need to expose it here, right? But I still feel like I want it here, because this particle effect info thingamajiggy, right? So if I have something like, what would that be? Ambient. Is it pollen? No, not really. Well, let's call it that anyway. Let's call it that. So, okay, so one more thing I want in here is actually to automate this memory allocation for the particle state, right? So then we just need to put this size into this this info as well, and that would be something like particle state size, right? Like that. So this is like the particle. Maybe we can call it particle effect definition. Maybe. Whatever, name is not important. So now we can just loop through all of these infos. and do this automatic. And I guess for that we also need to make turn this into some structure. Yeah. So let's call that maybe particle effect state, maybe. And in there we will keep track of how many particles we currently have of each effect, on this current effect, and the actual memory where the particle state is stored, right? So we'll have the count and the particles. Yeah. And we will have one of these states. For each effect. So we have the count here, right? Right now we have 2. Right, so now we can actually initialize these, I guess automatically, right? There's not going to be any duplication, so count will already be 0. Yeah, because we 0 initialize this whole particle system state, right? Yeah. We only need to, I guess, fetch this particle effect info. Like that. So now we have allocated the memory. Let's add some proper error handling here. Like that. Right, and we have to do some changes in the logic also. Obviously, I guess when we tick the particle system, I guess we just go through every effect we have, or every type of effect, and just call some custom implementation function, right? Yeah. So let's call it effect index, and go through every type of effect. Yeah. So we want a separate implementation function for that, and we could also put that inside of this effect info, right? I think that's kind of appropriate, actually. So we will basically have the data here for this specific effect. Let's maybe add a comment. So this is the footstep dust effect. Yeah, and then we will have the actual function to update the state of those particles. That would be something like tick footstep dust, right? And what we need, I feel like we just need this, right? We just need this particle effect state. Yeah, so maybe we should move this down, actually, because we no, let's just forward declare that, because we only need the pointer anyway. So that would be the state, right? I think that's all we need to update all particles. of that type. Right, and let's forward declare it here. Like that, and we should probably implement static functions at the bottom of the file. I think that's good. Oh, and maybe we can also just... we can just... We can do the same with this spawn function, right? Yes, we could do that. Yeah. We can do that later, maybe. But in here, we need the state, right? Somehow. So we'll get the state right now just hard-coded. We have the effect states, and we just get the footstep dust state. Yes. We have the count. Right, and this is gonna be untyped. We can do everything here on this line, I think. So we'll get the memory, cast it, and that should be fine. That's fine. And now, right, we need to do the exact same when we render. We need some kind of implementation for that as well. Like that. Yeah, I feel like I want to swap these though. That looks nicer, aesthetically speaking. So yeah, and this signature is going to be a bit different, right? The state is going to be read-only, because we want to convert this particle state into some GPU particles, right? And I think for now it should be fine to just have it like this, basically. We take in the state and we output some number of GPU particles. Well, the number of particles is going to be the number of GPU particles is going to be the same as the number of particles in the state. That's a restriction I'm going to make right now, but that seems fine. So that's the signature for that. Let's copy that code. I guess we can copy this tick first into this implementation. So we have the count in the state. Yeah, right. Okay, so we just pull out this what's it called? Footstep dust. So we'll have the particles here. We have to cast it, right? Well, we don't actually. Not implicitly, right? If it's a void. But I'll do that anyway. Okay, so then we can access it like that. Yeah, makes sense. I could make this a one-liner also, because I'm just pre-increment it, right? One-liner. Okay, and then we have the rendering part here. Yeah. Yes, yes. We just need that. We'll do the same thing here, actually. We'll just pull this out. And this was const, right? Well, it doesn't... Well, it matters for the count, I guess. Go through every particle. And output this GPU particle, right? Yes. So now in the ticking, all we have to do is, I guess we actually need to store these function pointers, right? So we'll have some kind of oh god, how do I make a function pointer? It's like this, right? It's like, so we have some kind of particles tick function, right? And this is the signature, like that. Yeah, and we have a render function. So we have this tick here. Well, yeah, I'm not sure. Like, I guess this is all preference, but like you can just not put the pointer here as well, right? And I think I kind of like this more. I think I like this more to have the pointer in here, and we'll have to. The render function as well. So in here, for this dust, we just assign these two now. Right. And basically, so when we're ticking, we have this info now for each effect type. And we have the, yeah, we're ticking, so we just need a tick function, right? Just take that and call it with this state. Oh, effect index. I think that's it. That's everything, right? Maybe I could make it a bit nicer, but just, I mean, pulling this out first, right? So we have the particle effect state, and we pass that into the tick function. Okay, and this is gonna be just basically identical in the rendering function, right? Except instead of tick, we're gonna call the render function, and now we need to do some extra trickery, right? A bit. Well, okay, this one is alright, this is only used, this is used for like issuing the draw call, right? But okay, so I made the restriction now that the render function is gonna output the same number of GPU particles as there are particle states, right? Or particles in the state. So we'll just use the count here. That's it. And the render function, right, that's different, right? I forgot to actually change the signature. Well, that's like that. So the render function takes the state as input and outputs a bunch of GPU particles. Yeah. Did I forget anything? Okay, that's completely wrong. It should be the size of this state. Alright, it compiles. However, I added this new effect. Let's just skip that for now. Okay, that works. That works. So now, yeah, if I want to now add a new kind of particle, right? All I have to do, well, all I have to do is duplicate all of this stuff, because I need some new state for this particle, and I wonder what that's gonna be actually. I wonder, let's just say for now, it's probably gonna have, okay, let's say that it has the same kind of things. Okay, so we have the, what is it called, ambient pollen. Ambient pollen particle. So we have that state. Yeah, and this is the exact same except for the name, obviously. Right. I feel like maybe I don't even need this like prefix, right? It feels a bit unnecessary. And I have a strong urge to just move these actual implementations into some separate file, actually. Maybe I'll do that later, because it's a bit messy to have it around here. But these are gonna want... Yeah, okay, so it's the exact same state right now. But it could be different, it could be. So, we have these pollen particles, and we need this different update. These tick and render functions. Right, and that's the only thing, right? Well, except for... So I only have to implement these two now. Well, except for the spawning, right? Okay, so the spawning, I also want to like add that here, right? So there should be an addition, or if the interface is getting big now. So we also have to implement some kind of spawn function, right? And we have this spawn, and let's move this out. Okay, so we'll make the API look like this instead. So we have this particle spawn data, which, yeah, I guess right now is only the position for now. Right. I think that's gonna be better, because then I can just pass this spawn data into this function. It was a bit unnecessary to have the actual effect in there as well. Okay, that makes sense. Makes sense. So now just implement this. Well, the logic is already implemented, right? It's just in a different place. Oh, maybe. I mean, I could just put the random number generator in this particle effect state, actually. I guess that's nice. You're always gonna need a random number generator, right? Let's put that there. Alright, so now when we spawn, we can just... oh, I changed the wrong signature. Okay, this is gone. So we don't call that manually anymore, we just can look at this effect info, right, using this effect. And this info now, okay, it doesn't yet. I forgot. I have to add the spawn function pointer as well. Right, and we just have to call this spawning function implementation, right? And we have to get the state. And the spawn data, that's it. Right, and we put the random number generator in the state. I think that's fine. Right, and I have to... this is getting a bit much, maybe I should just... do that. Alright, I forgot to change this, so this is the ambient pollen, right, and I need a spawn function implementation for that as well. Like that. This feels like a lot of it's like a lot of boilerplate, right? Still, like adding a new particle type. Like I have to do all logic myself. I think there should be some nice way to compose, to do some composition here later. So let's see. I guess the question is, do we still need the spawn function? Because I'm not gonna be spawning them through this API. And like, oh god, this is... I guess I need to spawn them at least once, maybe? Maybe I don't actually have to kill these particles. Let's see what we can come up with. Because like an ambient effect. Let's try something. I guess. Like I feel like I just want to spawn all particles at once, like one time, and then they can like figure out stuff themselves. Or like should some other system be responsible for spawning this? That is the question. I guess having some other system, I feel like that would be... Well, we can at least... Let's try to... do something like this. Okay, so when we spawn... Like, I really wonder if the spawning logic can be self-contained here. Because I guess, what do I want to do? I feel like I want to, like, spawn these particles along the surface, kinda, of the world. Right? Yeah, kinda. Kinda. And then the question is... I mean, because that surface lives somewhere, right? I guess one alternative is to pass the world geometry into this particle system, right? And then actually try to figure out those surface points in here. I feel like that's nice. And like have some constant number of particles. So I guess like when a particle dies, it just immediately finds a new position, right? And that means I need this. I need the world polygon data. But I could also just in the world just do that. It's difficult. Okay, I can try that first. Because I already have a spawning API, right? So I guess at some place we can just sample the surface, essentially, of the world and call this function at some points. Yeah, let's do that. Let's start off with that. So then the spawn function, I think that would just spawn one. Then, right. So spawn count would be 1. And I guess yeah, they would have some age then. Let's start with that. Yeah. And I guess we also... We should do some bounds checking here. So we don't... To just prevent us from writing out of bounds here. But whatever. Okay, so let's try something like... let's try not damping this, I guess, and... we can just use also the age to do some logic, right? I'm thinking something like moving the particle in a wave kind of way. Right, so let's say that we... let's do that later. Let's just see that we can get the spawning working, actually. Right, I changed the API. Like that. Okay, everything is still working. Okay, so like it feels very weird, but as a start, okay, let's just put the pollen spawning logic in the game also. Whatever. It probably shouldn't be here. It should be in the world, most likely. But it's easiest to do it here because I already have the spawning interface, so let's have some kind of pollen timer, right? And let's do it here also. So let's increment that by the delta time. Oh. And if it's above I don't know, yeah, 100 milliseconds. Then we should spawn something, right? So spawn some pollen. And so we have the okay, I really feel like this should be in the world. Okay, let's just fucking do that. Okay, so in that case, I guess we need some. Let's make a world tick update also. Why not? And that's just gonna take in the world, yeah. Like so. So instead of this. So let's put that here. Right, so the world is also going to now need this particles interface. I guess that's not too bad, maybe. And yeah, let's just pass it at creation time. And we're just gonna hold on to that, just like the Vulkan interface for later. Right, so now in the world we have this polygon that defines the surface of the world, right? And a very simple way, I guess, of sampling this, it wouldn't be very uniform, however, but let's just, we can improve that later, I guess. So, we can just, oh well, we can't use rand here. Okay, let's, I want to use the same random number generator I created for the particle system. So let's just make a new header for that. I guess we can call it well, rand. Where is rand? There's no like rand. No, it's in stud lib, right? Okay, so we can make a rand .h or maybe random.h. Okay, so we want this. Alright, so now we can use this firstly in the particles again. This rand.h. Right. And we also want this in the world now. To have some independent random number generation. We can use a global common one here, okay. So we just want to pick a random vertex, right? A vertex index. That world RNG, right? That is a random vertex, all right. And then we want to look at the edge from that vertex to the next one, right? Next, well, let's just okay. So we'll have let's call it A. Okay, so that's the position of the first vertex, and then the next vertex on that edge, just +1, and wrap that around as well. Alright, so A and B. So we want to pick some point between A and B, right? So we'll just do that with another random value. What am I doing? Like that, between 0 and 1, and we just lerp between A and B with that random factor. So that will be the spawn position of this effect, of this particle. Right, and we just have to add this tick function now. And let's see, the order of this will have to change a bit because we're passing the particle interface to the world creation now. Right. Let's see, here we tick everything. So maybe we want to tick the world first. It shouldn't matter that much, but like that. So now it should be spawning some stuff. I guess we can make these particles really big so that we notice them. lerp F. Wait, did I move that? Where did lerp F go? Oh, right, it's in. Wait, where is this error? Right, I moved that into back. Multiple definition. Oh, are you kidding me? I already have a random number generator. You fucking retard. Oh my god. Okay. Okay, I'll just move the ones I did into this one, I guess. All right. Move to trash. RNG is a better header name anyway. How could I forget? I forgot. No rule make target. We'll do a clean rebuild, I guess. All right. That spawning did work. So we are now finding random points on the world's surface, right, to spawn some particles on. That works. Okay. Let's change the color a bit. I want them to be white. Okay, they should live for a bit longer, I feel like. So, where is the lifetime? Here. Okay, so we'll take some random value. Between maybe, I feel like they should be live for a very long time. Let's say 5 seconds, 5 seconds, and 10, maybe. Looks cool. Okay, so I want it to be way slower. So maybe not 0, but so 0.005. Okay. That looks like something. We can scale them down now a bit. Okay, that's way too small. Way too small. So let's I could. Hmm. Let's see what that size looks like. Okay, that feels a bit... I don't want as much randomness on the x-axis here. Did I... oh, the position. Right, and the position, I don't want the position to be randomized at all, right? Okay. I was changing the wrong value. Alright. This looks nice, actually. It looks a bit magical. Looks a bit magical and ambience-like. Let's increase the lifetime even more, actually. Right, I would like to spawn a bit more. So, I mean, this is really unfortunate now. The spawning timer is like completely independent from the rest of the particle logic, right? Yeah. It feels like it somehow should be internal to the particle system, but I'll have to figure that out. So I want to spawn a bit more particles. Alright. Maybe I should reduce the actual, the vertical velocity. Let's see, velocity. Yeah, right. Even more. Even slower. That looks magical. Like a fairy tale. Okay, now I really want it to also use this velocity grid, right? Or this velocity vector field. They should sample that and like also follow the player vortex, right? Right, let's try that. Well, first, maybe I would also like to fade these out based on the lifetime. Right, but I feel like if I just lerp it using this same thing that we did, let's see, like we have that already here. So if I use this, I feel like it's gonna like maybe be a bit too well, let's see how it looks. maybe it's hard to see on stream. Oh, not really. Okay, not really. Okay, this looks nice. Maybe I should increase the velocity, minimum velocity a bit actually. What was it at? It is 0.1, right? Okay, 0.1. Let's make it 0.5. All right. Okay, so I want to actually have these particles sample this vector field that we have, that the player affects. So let's see how I would do that. I don't think we don't have a sampling function on the CPU right now, so I guess we'll do that first. We only have one for the GPU, right? So wait, is this set focus actually used? Okay, whatever. Don't get distracted. So we want to sample this. So we have wind sample, I guess, and we have some position at where we want to sample it. Yeah, and we will have to pass the wind also. So okay, so yes, that makes sense, and should be fairly simple, I think. Should be fairly simple. We already actually do sample it for this debug drawing of the vector field, which looks like this. Right. So we have this sampling it, so it's gonna be basically the same, right? Basically the same. So what are we doing here? Right, the index, the dy and dx. That's like the the global grid position signed, right? So we need this. And the only thing we have to figure out now is, well, basically this dx and dy. And I think that should be very simple. I guess it's basically just the position, right, divided by the resolution. I will try to floor that first, like this. So we know which cell index to sample from, right? That should be it. That should be it. I feel like... right, so let's try that. So in the particle system, we're going to need... we need this wind interface somehow, right? And I guess we can just pass that in when we create the particle system, not window, wind, right? Take the wind particles, create, update this, and we just need to store this then in here. for later, right? Store the wind. Right, and then inside, where we tick this ambient effect that we have, these small white particles, we want to sample this wind. However, the only argument we get into this tick function right now is this state, and I wonder if I should just add some additional one more parameter. I wonder. I mean, the simplest, I guess, would be to just pass the whole particle system, right? But that feels a bit wrong. I feel like I want to be more restrictive in what I pass there. But we can start by just passing the particle system. And that can be a const anyway, and I guess that's a bit restrictive, right? So in the tick function, we'll just pass the particle system as well, like that, and we have to update these implementations. First one and the second one. Right. Oh. Gosh. Okay. Wait. What would I call this? Wait. Hold on. Okay. So what would I call this that I would pass in? It's like some kind of maybe external state. So let's call it. Yeah. Let's make it like so. Let's say that it's like some particle. Yeah, particle well. External state. Yeah, okay, that's a bit long, but sure. Okay, so in here we want a pointer to the wind interface, so we can sample that. Right. Let's call it external. Yeah. Like so. What's the problem? Mismatch. All right. So when we tick this now, I can just sample. So we have this wind sample, right? Pass in the wind, and we know the position of the particle. I wonder if we should do it before or after moving it. It shouldn't matter much, right? Let's do it before. So we just want to add the velocity that we get from the wind sampling, and we most likely want to scale that down as well by some factor. Most likely. Okay. Now the only thing to the left is to right, we have to pass this external state. So let's create that external state. External. And that's going to be just this wind. That's simple. Just some like context, right? Some contextual data. Right, and now when we create the particle system, we have to pass this wind interface. And it doesn't seem to doesn't seem to be doing anything. I wonder if the sampling is wrong, or if I just scaled it down too much. So I'm sampling the position. Let's try scaling it up, I guess. Yeah, it's okay. It's most likely sampling the wind wrong somehow. So let's check that function. Okay, that's probably the issue. Yeah, and now they just completely disappear, so that that velocity is way too high now. So yeah, I mean, I probably have to scale it by the delta time, right? So let's say delta time scaled by some factor, right? Okay, that's still way too high, okay. That's more acceptable. Very subtle, though. Okay, that's pretty cool. And we can let's see, we can disable this debug rendering because it's a bit hard to see the actual particles. So now these particles also get caught in my vortex, right? Oh. That looks pretty cool, actually. Maybe it's a bit much, I don't know. No. I don't know, I like it. But maybe it's a bit too much, yeah. Maybe a little bit too much. Little bit, very little though. I wanted like uniform kind of with the grass pushback, right? Yeah, and we should definitely get some bilinear sampling in here. Yeah, we can try to get some bilinear sampling maybe. Maybe I should scale it down a bit more. I don't know. Like, no, maybe if I get bilinear filtering in, maybe that will look better. I increased the spawn rate a tiny bit, and like there are some issues with the uniformity of like the distribution of these particles, right? because at first I pick a random edge. So I mean what that does right off the bat is it basically prioritizes small edges, right? And there is a pretty simple fix to that. Well, kinda. You can sort the edges, yeah, I think you just have to compute the like prefix sum of the probabilities in some way, right? And then you pick a random value between 0 and 1, and you just do a linear search through the edges. So that could be fixed, right? But for now, yeah, I think it's pretty noticeable also, right? Like there's more being spawned here, and like the density, the edge density is higher here on this in this place rather than here, right? Okay. By linear filtering then. Should be easy. I already did it on the GPU, right? So let's see. We have the sample function. Right, should be easy. So let's make that a conditional. Alright, so if we're doing bilinear, at first thing is to subtract that, right? Let's see. We can actually just look at the GPU implementation side by side. Oh well, for you on stream, it's I can put it here maybe. Right, so we need to get the fractional part, right? Right, the fractional, yes. Okay. Let's call it right, okay. I don't have a division, right, but multiplication should work just as well. Right, so the cell size, well, it should be a scale, right? So we scale it down by that. So we have the float grid position, right? And how are we using that in the normal case? Yeah, it's just flooring it, right? So I guess we could yeah, do that and move this out. So we always want the float grid position, right? And this would be the top left, right? So we are flooring, yeah. Right, after we divide. So it's in grid space, yeah, minus half a grid cell. And yeah, we can get the bilinear. The bilinear factors, and we will implement this getting a fractional part of a floating point number. And what is that? Vector frac. Right, so how to implement that? I guess I don't think there's like a frac in the standard math library, like just right off, no. But there is f mod f, right? And that is that identical? Wait, what about when you're in the negative quadrant, right? Oh, does this even work on the GPU now, in the negative? Maybe there's some bug there, right? Because if you take the fractional part of a negative, that's like inverted, right? That's inverted. Returns the fractional or decimal part. Yeah, so if we do that on a negative number, like that's gonna flip directions essentially of the bilinear filtering. That is annoying. Can I wait. So a different way, I guess, might be to right, you can, I guess, instead does it improve if you just because you can take the if you take the floor, you floor the value, and then take the number minus the floor of that. Well, to start off, let's just implement this anyway. Let's implement this anyway. So for now, just take the floating point modulo. I think that's, is that equivalent? Is that equivalent? That is the question. So part of float. See. Wait, what? Okay. All right, and then I'll just can I pass a dummy to this? Can I pass a dummy null pointer? Can I pass a null? Can I pass a null? It doesn't mention anything, so I'm gonna assume that that is not valid. Okay, so let's call it dummy. Yes. Okay. Like that. Right. Yes. So back to the wind sampling. Now we can take the fractional part and get the bilinear factors, like the shader. And the top left is gonna be this. It's gonna be this. So right. Okay. Oh, okay. So let's see how we want to do this. So index 00 is gonna be that, and I10 is gonna be that, 01. Let's actually make this pretty. 001, 11, 11. All right. Right, we have the indices. Yeah. And now we have the velocity values for each one of those. Simply like that. And now I will steal this bilinear filtering code. So right, we want to lerp two vec2s. That should be it. I think maybe it looks like it's working. Maybe it's sampling the right area, at least, like somewhat. Yeah. I could try to, make the grid more precise, right? So by, I guess, decreasing the cell size. I can take a look at the debug rendering though first. So we have this. Yeah, it feels a bit smaller, or like the cells are a bit big right now, right? But okay, maybe it really doesn't matter, I guess. But like, I wanna try to see what the difference is, see what the difference could be. Okay, why not? Why not? And wait, how many? I have 64. 64 times 64, that's 256, right? It would be nice to start profiling soon, maybe, but like 256, and like, okay, if I increase to the next power of 2, what's that? 128 times 128, 16k, right? 16k cells. But like, okay, so 64 times 0.25, how much area are we actually covering? 16. Okay, I can zoom out also and see. I mean, seems to be good enough right now, right, for this. I guess, except if I do this. It's outside of the screen, but my player is the only thing like affecting anything right now anyway, so... Oh wait, I actually wanna do an experiment, wait. Because it's wrapping around, right? So I wonder if I would see... It should be like looping around, right? I wonder if I can see that. If I zoom out the camera. A bunch. Yeah. You can see the wrapping here. My player is affecting the grass here as well. Because the grid is just wrapping around, like the sampling of it. So okay, maybe... Oh, my... Well, hello? My GPU died again, almost. Close call. Okay. Maybe the cells shouldn't be this small, maybe. It shouldn't, like, 0.4, let's say, that's a bit smaller at least. Let's disable the debug rendering also for now. Again. Alright, I like the visuals of this anyway. Looks pretty cool. So the particles are now sampling the wind grid. Right. I do wonder. It's pretty hard to like verify the bilinear filtering, really, because I suspect that it is wrong. because the bilinear factors, just taking the fractional part, I'm pretty sure that's not gonna work. Because then the direction flips as soon as you cross into the negative, right? Because then the larger, like the bilinear factors are flipped in that case. I assume that they're gonna like follow the axis, right? It's always gonna go from left to right and bottom to up, right? But I assume this doesn't work. But it's hard to tell. I think it would be useful to maybe we could print how many particles we actually have, and we should actually bounce check this as well. So let's I guess we can, after every tick we could just print this, I guess. So it would be nice to have text rendering functionality in the game, actually. Well, hello. Oh, it's stud.io, right? Stud.io. Let's see. Particle count, and that will be for a specific effect, right? So the effect index will have some particle count in the state. Let's see actually how many we have. It would be interesting. It's going up, going up. Alright, so it's kind of equalizing at 300 right now. 300. I could have a bunch more. Let's see, if I decrease this to 30, and I can just increase this limit preliminarily also, let's say 4K. So that's 400 instead. Right, I wanted to add some more interesting movement to these. Right now they just follow an exact linear path, except for when I jump around, right, obviously. But I want to make them like wiggle around, maybe. Right. So if I update the logic here, so we need a tick. Right, we can. I guess we can just use the age for that, right? So if we just sample, take like the sine, right, of the age, we should get some wiggling going on. I just wonder how fast this is gonna wiggle. We can scale it down a bit to check. So let's say that we just move the position a bit in the x direction based on this wiggling, and it should probably be scaled down a lot. Let's see. Okay, that's way too fast. I think that's way too fast. So what's the problem? Is it just it's the speed of this, right? It's the speed of this. Okay, that's also way too much. Yes, way too much. Wait. So I mean, is the the like speed might be fine now, but we have to decrease the actual impact. That's a bit too much still, right? Yeah. Well, maybe. Yeah. So decrease that a bit, and maybe that's still too much. Magic values everywhere. Right. Okay, now the effect is either too small or this is too slow now. Yeah, it's not doing anything. But what? Wait, what? Did I? Is this way too slow or? Okay, I think that was way too slow. Let's go with that maybe. Oh. Okay, that looks like looks pretty good, maybe. Looks like some fake kind of wind, right? Acting on these particles. I think it looks cool. Now I feel like the wind grid influence is too low. But nah. I think I should actually reject these edges. I should probably check if the when spawning this whatever it is, fairy dust, pollen, magic pollen, I should check that the surface is pointing up, because right now they're spawning down here, you see, and on these edges they should probably only spawn where the flowers are spawning also. And I have some check somewhere. Plant, yeah. So, right. I just have to check this. So we'll just reject those samples. So the vector towards B, yeah, from A to B. And in that case, I do an if, right? So let's just invert this, I guess, and only spawn if the normal is pointing up. That works. And that's gonna decrease the number, yeah, drastically. It almost cut it in half, which I guess makes sense. I guess statistically, I guess half of the surface statistically will be pointing down, right? And the other half will be pointing up. Right. Oops. I guess I can try. I can build a bit, maybe. I guess I should maybe restrict the spawning inside of some radius from the player, right? Maybe. Because if this world gets larger and larger, then... Like, well, first of all, the spawn rate is gonna have to adapt somehow to, like, account for, I guess, the total surface area of the level, right? To have some kind of consistency. Because now, if I okay, let me save. I think I saved it. So let's, if I just start deleting vertices now, like it's gonna be more and more dense, right? The density of these particles. Because the spawn rate is fixed, right? I spawn a fixed number of these particles every second. So now that there's less surface to sample, right? There's gonna be a lot more. It's a lot more densely packed, right? So I guess you would have to want to account for that somehow. I mean, it's easy, I guess, to compute the total surface area of this this polygon, and like weigh it somehow by looking at the total length of the shape, right? Maybe I could do that. That's kind of similar to how I did it with the flowers, actually, because this density is uniform, right? And it doesn't matter if the edge is this small, right? Or it kind of adapts, right? And I guess it's very similar, if not identical, to change the spawn rate of these particles also. But I wonder if I wanted to do that, because like if the player is here, do I actually want to spawn this anyway? Probably not. So yeah, it should be different somehow. Oh wait, no, wait, no. Oh. It looks like the bilinear filtering is broken, kinda, right? It seems like it to me. Now what? Okay, there's only 300 particles now, so I will increase the spawn rate once again, because I added more surface area. Okay, what could I do next? What kind of easy particle could I add? Maybe actually. Maybe I want to actually add the depth into the particle data that we use for rendering. Maybe. Right now it's still hard-coded. I want to see how it looks if I move it to the front, actually. I kind of want it, at least this dirt, to be in front, but I'm not sure. It should probably be semi-transparent, at least. It's a bit jarring, like it looks like literal shit, kind of, instead of dirt. But if I had them behind the grass, it was barely visible. So, this pollen stuff, those should definitely be behind, at least. And it's I'm kinda out of damn it. I mean, I really should be using an integer depth buffer anyway. I feel like that would make sense, because like in a 2D game you want like you basically have layers of things, right? And I don't think like representing those layers as some floating point value makes sense at all. But there is like an integer depth buffer format, right, in Vulkan. Let's check. So right now we are using 32-bit signed float. Totally unnecessary. Right, so there is a D16U norm, but so it's U norm. Right, so what does that mean for me? Really, I still have to figure out the floating point value, right? When I output it in the shader, I think. So it's gonna depend on the Z value of this position, right? And that's still a float. That's still a float. But that's probably fine. Well, I can try just changing the format and see what happens, right? And do some experiments, maybe. Right. Where was that? Render targets, right. So we want D16 U-norm. Right, maybe we want a stencil in the future. Maybe. Are those the only depth formats, actually? These are the only ones, I assume. Yeah, so D16 U-norm. I hope that's as well supported as a float. Let's see what happens. It should just work, right? Should just work, and it does. Yeah. No validation errors. Okay, so that's the easy part, I guess. And then, right. Like my game is probably not gonna need more than 256 layers, right? That would be nice, because then in that case I can just put the depth value, or I guess basically the layer index, right? The layer index. I can just put that in the alpha channel of the color of the particle, right? Because, or wait, I guess I am gonna use the color, right? Because I guess I do want transparency in the future, probably. Okay, so that's not gonna work. However, I can probably just quantize the scale anyway. So if I maybe use 24 bits for the size and have some reasonable range, right? That might be fine, because I really don't want to make this larger than 16 bytes if I don't have to. Well, first, I guess I have some changes to commit, right? Maybe, and let's remove this printing for now. All right. So what have I done? Yeah, I haven't committed since I added this new particle, right? And this new ambient particle, right? I don't know, ambient fairy dust forest particle, and wind sampling, right? Wind grid sampling inside particle system. Sure. Right, I could try getting the layer in here, but I guess, I mean, or do I care? Do I care is the question, right? Yeah, I do care. Well, I mean, the packing is gonna take some cycles also, right? But let's say we have the size and layer, right? We have the size and the layer. And maybe we'll add a comment, I guess. So the size is going to be, how do you do this? It's the size is the first 24 bits, right? And then the layer is the last 8 bits. Yeah, and so size, what's the largest possible particle you could want, right? Like 24 bits is probably plenty. well, if the size is gonna like move around slightly, I guess it might be visible actually, the quantization. But let's think about that, I guess. Well, even if we make it 16 bits, that's 65,000 different sizes, right? So, yeah, let's say, can you do math with hexadecimal in DuckDuckGo? So if I divide, yeah, let's say, well, the largest possible particle. Like, I wouldn't say like more than 2 meters, right? Or 2 meters for a single particle, that's like plenty, right? Even 1 meter, probably. Okay, wait. Okay, let's make it 1 meter. That's gonna be like the absolute easiest, right? Doesn't require any scaling at all. So I actually don't know this value by hand. Okay, 65, 535. Okay, that is plenty. That's plenty. What is that even? It's like so this would be a centimeter. So it's 15 millimeter precision on the scaling of a particle, right? That's plenty. So we will do 16 actually to start with. So 16 to 23, right? Yeah, and we have unused. Let's try that. Sure. Right, so now, though, we're gonna need some function to pack this value, right? Right, we can't just set the size anymore, which is pretty unfortunate. So, let's call that pack. I wonder how explicit I have to be with names, right? It's only gonna be like a static function, right? Let's call it pack size and layer. Maybe that's too explicit. Pack size layer. No, that sounds strange. Let's keep the and. So like that, right? Let's implement this actually first. I'm just gonna return a uint, right? So we want the size, yeah, in meters, right? Or in units. Yeah. Okay. This should actually be half size, because in the shader we divide the size or whatever. We're basically losing half of the precision now, but who cares? So we have the size and the layer. Right, and this should be pretty simple, I guess. Let's assert. Don't know how costly that's gonna be actually to assert every single packing, but we'll see. So the size has to be within the 0 to 1 range, right? And then we just multiply that by, we don't even have to cast that, by this, right? Right. So that's that, and that's in the bottom bits, right? Right. And the layer has to be less than 256. Well, let's say FF, right? And we pack that after those 16 bits, right? And of course, right, I kind of like being explicit about that, I think. Okay. Well, if this is 1, this is gonna be out of bounds, right? So it has to be 1 less. 1 less, like that, right? Or am I wrong about that? No, wait, never mind. Right, this is the max value. Okay, that's fine, right? That should be it. I think this search will potentially ruin performance. So let's see, size and layer. This is going to be pretty... Okay, I should change this later. I feel like it would be a lot better to still have some struct, right? Where I can put in these things separately, and then have some function to pack an entire particle, right? Instead of packing the individual fields manually right now in every single place, I can improve this a lot. Right, so for trying this out, I want the pollen stuff to be behind, so let's make that layer 1. That should be behind in that case. So... Wait, why did I... Alright, I have this debug particle, right? Of course. Right, and I have to unpack it in the shader, so there's no size anymore, right? Let's unpack particle size. Maybe we should put that in the same function. Nah, let's not. Okay, so to unpack the size, we just take the bottom 16 bits, right? Yeah, and divide that by that. Right. It's just a unorm value, basically, right? Right, and we want to unpack the layer as well, and I guess we want that result to be a uint, I guess, and that's just gonna be this, right? Like that. Yes, makes sense. Okay, and it's not gonna be size layer, right? Okay, so instead of using the size directly, we have to say size and layer. Okay, let's see if everything looks fine. I think it does. It does. Okay, so that works. Packing works. First try. So now the depth is going to depend on the layer somehow. And I really wonder if we... I think we can just set the depth value of this, right? Like, right? Let's try anyway. So we will unpack the layer. So that's the integer, no, the layer index now as an integer, right? So we want to convert it to float. because it's unorm, and it's unorm 16. So I guess all that means, I guess it's just this, right? So I guess it's that. I guess so. Like, I have no idea about the precision implications here, right? I think it works, literally. I think it works. I mean, these are at least behind the grass, right? Which is what I wanted. So they're on the a layer index higher, right? And these footsteps are in front, which is what I wanted as well. Okay, so that works. So I can specify some integer layer that I want a particle to exist on, right? Right. So just for trying out, I guess. So if I change this to 0 again, it should be in front. Yeah, it's in front of the grass. No. Yes. Okay. I have no idea about like the precision of this. Converting my int to a unorm. To a unorm float. Well, I guess like, okay, well, I guess it's fine. Like the what's the mantissa of a float? All right. Like I basically have the whole mantissa, right? If it's between 0 and 1, like, is that how it works? Probably, right? There's at least, there's even more than 16 bits of mantissa. It should be fine. Oops, I should add control C controls. Okay, that's cool, I guess. So I can put particles on a specific layer, rendering layer. Right. I wonder if I want to define these layers somehow. I mean, name them, right? But I wonder what they would be called, because I want some parallax layers in the future. But then, like, I probably want some number of layers like on top of that, right? Like for each parallax layer, you probably also want to have a couple more layers. Maybe. This dirt effect is a bit much, actually. Maybe it shouldn't be shooting up so much. Let's change that. So there's some range here, yeah. There's some range. Let's make that half. Okay, that's a bit better. It's not as intrusive. I feel like the size should it should be a bit smaller. Yeah, I feel like I should add some kind of player sprite soon, or model. I have no idea how I want that to look. like I don't want some pixel art at least. I don't know. Since everything else is made out of polygons, right? I want to keep it that way. So I guess my idea is to have some kind of skinned player, like basically a model but in 2D, right? Maybe. I mean, my it could still be textures, I guess. I just don't want it to be pixel art, I think. If it's high enough resolution, I guess it's fine. I'm thinking something like Limbo. Something like that. I like the art style of Limbo. Let me find something like this. Because that's basically a rigged model, right? Except it's just in 2D. So it's definitely possible, right? Could be cool. Is that a turkey? What the fuck is that? Looks like a turkey. Induku. Nice. Induk. Why is that a type of turkey? Is that a what the fuck is that? Let's Google. What? It's a diplomat. No, it's a diplomat. American diplomat. Tage. So, oh, I can't do underscore T, right? That's illegal. Illegal if it's not a type. I'm wondering. Like, there's a lot of redundancy, or not redundancy. like I have two types of particles, and the logic is kind of similar. Like, I could definitely split this up into some kind of do some kind of composition, right? Some kind of composition. For example, this wind sampling. That could just be some kind of flag, right? You could just say that, yes, I want this particle effect to be affected by the wind grid, right? That could be some kind of like some float, I guess. Like how much you want to be influenced by the wind grid, something like that. Instead of, because now if I want to sample the wind grid in more particles, like I actually have to add that code, right? And like, sure, I could make this a lot better by just creating a simpler function, right? Something like, let's say, ever worked with 3D? Yes, I have. In some hobby projects I did, but for work I also do 3D stuff on a game. Yeah, but I think like every time I've done some hobby 3D project, I mean, it's really hard to finish actually, and like doing this 2D stuff with Vulkan is pretty interesting still. It's pretty interesting still, and I mean, there's not. There is some difference, sure, but oh, left and right. I actually have no idea. Well, I know what it means, right? But I'm not gonna be able to say anything more specific than that. Like, I know what. I guess if I saw a well, no, it's really, I can't go into specifics. I mean, I know that you like want to use different kinds of different code. Like, you have to tailor, I guess, like the projection matrices and stuff, depending on which one you're using. But I really can't, like, when because I have 3D projects where I did create my own matrix functions and stuff like that, right? But I don't even know if I'm left-handed or right-handed, right? I just tried something until it worked, right? Because it's 50-50, right? Anyway, so yeah, I'm not that like good at linear algebra, but yeah. So I guess, I mean, I could make this simpler, because right now it looks like this, right? I could just make a function for this that's called, I guess, like yeah, sample wind, and I have the position here, and I get out a new position, right? And I just have to pass in the external state. And also, I guess, some scale, some, or amount maybe, and just do this, right? Return this external wind pose, right, pose, and the amount, or factor, well, amount, or whatever. So I can just replace this whole thingy. Yeah, what this game is about is right now nothing. I'm mostly having fun with graphics actually, like doing particles and stuff. I have something in my mind, but nothing really concrete. I guess we'll just see what happens, right? It's at least gonna be some kind of platformer. I can tell you that much. Yeah. But yeah, I'm not really focusing on the gameplay right now. I want to get some graphics going first. Yeah. The physics is extremely janky right now. If I like walk, I get stuck in the ground. It's horrible. But yeah, I don't know. I guess I can make this even simpler also by just modifying the position like this. That will make it even simpler. Right. So maybe that's not too bad now. I mean, if I have more particles that want to sample the wind, right, I can just add this one function call now. But still, there are a lot of similarities between particles anyway. Maybe I'll figure it out once I have enough particles. Can find maybe some abstraction instead of functions. We'll see. We'll see. Right now the game is about jumping around and getting stuck in walls and looking at the pretty grass movement. And this is already it is actually pretty satisfying to just jump around in this shit. Except that I get stuck right in the ground, which is unfortunate. Maybe I should look into improving that. I'm actually not sure, like, let me debug draw the collision data. So we have these triangles, right, that I am checking a collision against. So I have a function to collide a rectangle against a triangle, and I do that for every triangle. Pretty simple, right? However, yeah, you can see the problems here, right? Maybe it's easy to fix, but I'm starting to think that maybe I can just collide with the initial polygon instead. Instead of first just making triangles out of it and then colliding with it, right? I wonder if it would be more difficult to actually just collide against the original polygon or not. I wonder. It's possible. Right. But I do think that's enough for today. I can't think of anything quick and easy to implement, really. Okay, I didn't commit the layer thingy. Add layer index to particle, GPU particle. Let's say that. Right. And unorm 16 depth buffer. Okay, but that's it. I like the progress though. It's fun to jump around. It's pretty juicy actually. But that's it for now. See you later, alligator.